Okay, question 3 of the term assessment 2 corrections. Okay, we're looking at basicity. So PKB values are given to you. Again, please take note PKB equals negative log KB, which means as a result, if you have a higher KB, you correspondingly have a lower PKB. So the lower the PKB, higher the KB, it will imply that it's a stronger base. Okay, so in this case, Na is a stronger base. This is a weaker base. And 12.22 will indicate that this is the weakest base. So recall what does basicity represent. Basicity is basically the availability of a lone pair on the N atom, because N atom is lone pair. I've drawn the lone pair so you see, to accept a proton. Alright, basically I'm using a Bronsted-Lowry definition. Okay, to accept a proton. Okay, proton acceptor. So in this case, we're supposed to explain for why there are two different PKB values of 2-amino-benzylamine, this compound here. So why are there two PKB values for Na and Nb respectively? So Na has a much lower PKB value because it's a stronger base. So why is Na a stronger base than Nb? So you can see Nb itself is directly adjacent next to the benzene ring. So what happens? The lone pair on electrons on Nb atom can be delocalized into the benzene ring, and therefore this results in lone pair not being likely to accept a proton, because why? The electron density has decreased. Okay, you do not see me using terms like negative charge. Is there any negative charge? There is no negative charge. Is this compound charged? No, there's no charge at all. So this is wrong. Many of you use negative charge. Okay, so electron pair already delocalized in the benzene ring. The key term you don't use is example, if the electron density is decreased and therefore it's less likely to accept a proton. Now, conversely, on Na on this N atom, you now have a big R group. Okay, this lone pair here cannot be delocalized in the benzene ring because it's separated by this CH2 carbon. This CH2 carbon, this carbon here is sp3. So this lone pair cannot be delocalized in the benzene ring. So in this case, what do we treat this? We treat this as a big R group, and R groups are electron donating group. So this electron donating R group, if you don't know this is called benzyl group, you can just call this R group. This R group includes CH2, NH2. Alright, which increases the electron density of the lone pair on Na atom, and therefore the lone pair on N is more available to accept a proton, and therefore Na is more basic. Okay, so a 2-mark response explaining one for each. Why Nb is less basic, why Na is more basic. Okay, so that's part 1. Part 2, we're supposed to suggest a reason for the significant larger PKB value observed for diphenylamine. So in this case, you can see diphenylamine, this lone pair is now adjacent to 2 benzene ring. So there is a greater extent of delocalization. So as a result, the lone pair is even less available to accept a proton. So a simple reason like this will be sufficient. Alright, so key idea is to compare the extent of delocalization of lone pair of electrons into the benzene ring. Okay? So again, this concept, it's mentioned in the lecture notes. This is for your, if you draw a comparison, you have electron donating R group, this is your N, A, electron donating group, and then phenylamine, and B. Alright? So you can see the phrasing here, similar. Okay, not testing you things that are beyond your syllabus. It's just basically basic recall. Now, we're moving on to synthesis. We see that benzoyl chloride can be formed 2-amino-benzylamine via a 4-step process. And in this case, you're just supposed to fill in the blanks given to you. So if you take a look at the reaction, we have acyl chloride forming this. And then in between, I can see that it can involve benzylamine. So think about it. You can either think backwards or think forward. So if you take a look at this, okay, one quick way to look at this, CH2NH2, CH2NH2 with NH2 group. So which means you basically have to do the change of this NH2 group. One quick way to think of it, the only reaction to introduce a N-containing group onto the benzene ring will be to do an electrophilic sub-reaction involving an NO2. So that's what I do. Okay, so NO2, I know that NO2 can be easily converted to NH2. Okay, so back thinking, right? I look at this target molecule. I look at what's given to me. The main difference is the NH2. There's no reaction that substitute NH2 directly. So the only way to introduce something on the benzene ring that can be reduced to NH2 will be NO2. Okay. Again, many of you all propose weird reactions involving substituting chlorine and replacing Cl with ammonia. Alright, that's not possible. Again, halogenoarenes cannot undergo nucleophilic sub. So this is what I'm saying. Some of you propose changing, instead of substituting with NO2, you substitute with Cl, and then when you do this reaction, okay, that means you replace basically the Cl with the NH2. There's no such reaction, because why? For the same reason we say your halogenoarene cannot undergo nucleophilic sub. NH2, your ammonia cannot replace your Cl in nucleophilic sub reaction. Okay, so please learn your reagents conditions well, because and type of reactions well, because if not, you can't do simple synthesis questions like this. Okay, so this process will basically use a tin excess con HCl, heat followed by NaOH equals. This reagents condition is very unique. We mentioned this many times to reduce your nitro group, your NO2 group to NH2. Now to introduce the NO2 group here into the benzene ring, basically you make use of con H2SO4 and con NHNO3. Okay, you can view this like a methyl benzene, similar to methyl benzene, right? Okay, our group. So whether you write here or not, it's not important. We give BOD for that. But importantly, you need to use concentrated condition. This is not your phenol. Only phenol and phenylamine you can use aqueous. Alright. Then now we come to the question that how do I join the COCl to get this? So you think about it. Alright, now thinking backwards is not useful, and now think forward. There's only very few reactions that the acyl chloride can undergo. One, nucleophilic acyl sub. Condensation reaction to form amides, esters, or hydrolysis reaction to form carboxylic acid. So in terms of the reactions, very limited. So to form an amine, alright, if you think about the reactions, you definitely need to form what we call an amide, because amides can be reduced to form amines directly. So if you think backwards, amine, amides. Alright, so you use lithium aluminum hydride, your amide CONH2 becomes CH2NH2. Alright, so remember your only lithium aluminum hydride can reduce amide. None of the other reducing agents can reduce your amides. Okay, hydrogen gas definitely cannot reduce your amides. So how do you form your amides from the acyl chloride? You make use of NH3 gas, condensation reaction. The ammonia aqueous will not work because the aqueous medium will hydrolyze the acyl chloride. Now many of you propose weird reactions like this. Okay, there is no such. You can't have nitrile benzene. Okay, this is not possible. If you just think about it, how do you get this compound to start off with? It's extremely difficult. Okay, you need a Cn minus to attack a benzene ring. That's not likely to happen. Okay? So, the last part is C. It's again a book question. You have two acidic functional groups. So, part A we test on acidity. Part C we test on acidity. We look at carboxylic acid functional group and then phenol. So in this case, the question was very specific. They did not ask you to compare the acidity, but they will tell you, okay, carboxylic acid is more acidic than phenol, so explain why. So in this case, both phenoxide and carboxylates are resonance stabilized. So again, we are looking at the conjugate base. The concept of acidity is always on the stability of the conjugate base. So your phenoxide ion, the conjugate base of phenol, and a carboxylate anion, which is the conjugate base of your carboxylic acid. Both of them have resonance stabilization. Okay, so again, now it's the comparison, which is more stable. In this case, carboxylate is more stable than phenoxide. Why? Because the carboxylate has delocalization of a negative charge across this C atom and the two oxygen atoms. important words, 2 electronegative oxygen atom. This is to show why this dispersal of charge is more. Right, and as a result, negative charge is more dispersed than that of phenoxide. So if the carboxylate ion is more stable than the phenoxide ion, there's a greater tendency for a carboxylic acid, alright, to dissociate. Okay, again, many of you are using terms like the carboxylic acid, the carboxylate interchangeably. That's wrong. You need to be very specific, which is your conjugate base, which is your acid. Where can you find this? This is nothing new again. Your attention to details in your lecture notes is very, very poor. Page 13, exactly same comparison. So look at it. The delocalization of negative charge is over the C, and both electronegative O atoms in the carboxylate anion. Negative charge more dispersed than that of the phenoxide ion. Carboxylate anion more stable than the phenoxide ion. Right, these are just simply marking points. Alright. In this case, there is no value in going through phenol, because phenol, explaining the stability of phenol, doesn't help you account for this explanation. Alright, unless you have alcohol, then you need to show why phenoxide is more stable than your alkoxide. Okay, so with that, I'm done with question 3.